You're in the back seat of a car. It's a long road trip. You're comfortable. You've got a great book, maybe some snacks. Life is good. 20 minutes in, something shifts. Your stomach gets heavy. There's a weird warmth spreading behind your eyes. Saliva starts pooling in your mouth. You put the book down. Too late. The damage is done. Welcome to Briefly Science. And today we're going to figure out why something as innocent as reading in a moving car turns your body against you. And in doing so, we're going to take a tour through one of the most interesting misunderstandings in your entire nervous system. Because here's the truth. You're not getting sick because of the car. You're not getting sick because of the book. You're getting sick because your brain genuinely, sincerely believes you've been poisoned. Let's back up. Your brain runs a very specific operation at all times, every second of your life. It tries to figure out where you are in space, how fast you're moving, and whether you're about to fall over. And to do this, it pulls data from three completely separate systems. Your eyes, which report what you're seeing, your muscles and joints, which report your body's position, and deep inside each of your ears, a tiny, extraordinary organ called the vestibular system. Now, the vestibular system is, it's kind of insane. Buried inside your inner ear are two completely different types of sensors. First, there are the semicircular canals, three fluid-filled loops arranged in three different planes, like the X, Y, and Z axes of a gyroscope. When you rotate your head, left, right, up, down, tilted, fluid sloshes around those canals, and tiny hair cells feel the movement and fire signals to your brain. This is how you know you're spinning. It's elegant. It's basically a biological gyroscope that evolution has been refining for 500 million years. The second type of sensor is called the otolith organs. These detect linear acceleration, forward, backward, up, down, and they do it using actual tiny crystals of calcium carbonate called otoconia, sitting on a bed of jelly covered in hair cells. When you accelerate, those crystals shift, those hairs bend. Your brain knows you're moving forward, or that gravity is pulling you down. It's an accelerometer made of crystals and jelly, inside your skull. Wild. Together, these two systems give your brain a continuous, real-time feed of exactly how your body is oriented and moving through space. And under normal conditions, walking, running, climbing, being a primate, doing primate things, the vestibular system and your eyes agree. Perfectly, all the time. That's the key word. They agree. When you're walking through a forest, your eyes see the trees shifting past you, and your inner ear confirms, yes, we are moving through space. When you turn your head, your eyes see the world swing into view, and your semicircular canals confirm, yes, we just rotated. The two systems talk constantly, and when they agree, your brain is happy, serene, not even a little suspicious. But now put yourself back in that car, with that book. Your eyes are locked onto the page. From your visual system's perspective, you are sitting completely still. The words aren't moving. The book isn't moving. You, from a visual standpoint, are stationary. Your eyes are confidently reporting. Nothing is happening. No movement here. Everything is fine. But your inner ear is losing its mind. The car hits a curve, and your otolith crystals slide sideways. The car bounces over a crack in the road, and your semicircular canals feel it. The car accelerates, decelerates, sways. And every single one of those movements gets registered precisely and accurately by your vestibular system. Your inner ear is screaming, "We are moving. There is movement happening. What is going on?" And your brain is receiving two completely contradictory reports at the same time. Eyes not moving. Inner ear definitely moving. This is called sensory conflict, and your brain absolutely cannot tolerate it. It needs a model of reality that's consistent. It needs the data to match up. And when it doesn't, your brain doesn't just shrug and move on. It starts asking a very specific question, a very old question. Why would my senses be giving me completely contradictory information? And here's where it gets fascinating. Throughout the vast, vast majority of human evolution and animal evolution before that, There was really only one circumstance that caused your senses to wildly disagree with each other. Your visual system says you're still, but your body says you're moving, or your inner ear says things are tilting one way, but your eyes say something different. That scenario in nature almost always meant one thing: you had eaten something you shouldn't have. A neurotoxin, a hallucinogenic plant, a mushroom that looked totally fine but was absolutely not fine. Many natural poisons attack the nervous system and specifically disrupt the way sensory information is processed and integrated. And one of the fastest, most reliable symptoms of neurotoxin ingestion is sensory confusion. Your perceptions start to disagree with reality. So your brain, over millions of years, learned a rule of thumb. Conflicting sensory data means possible poisoning. And when possible poisoning is detected, the response is immediate, automatic, and non-negotiable. Get whatever you ate out, now. This is the poison detection hypothesis, first proposed by biologist Michael Treisman in 1977, and it's currently the most widely accepted explanation for why motion sickness exists. The evolutionary machinery that causes you to feel sick in a car is the same machinery that would have saved your ancient ancestors' life after eating the wrong berries. It's a backup toxin detection system, and it is being triggered by something your ancestors never encountered: a metal box on wheels moving at 60 miles per hour while you try to read a paperback. You're not sick. Your brain just hasn't updated its software. I mean, think about what's happening in your body during motion sickness. And honestly, it's a perfectly calibrated emergency response. Your saliva increases, preparing to neutralize stomach acid. Your skin goes pale as your body diverts circulation inward. You start sweating. Your stomach churns. All of it is tuned exactly for one purpose: purging a potential toxin as efficiently as possible. Your entire physiology is mobilizing against a threat that doesn't exist. There's something almost respectfully absurd about it. Now let's zoom in on the vulnerability question, because this is where it gets really interesting. Not everyone gets motion sick equally. Children between roughly 2 and 12 years old are the most susceptible, probably because their vestibular systems are still calibrating and their brains haven't built up strong models of what normal movement feels like. Women are more frequently affected than men, influenced partly by hormonal factors, with menstruation and pregnancy both increasing susceptibility. People who experience migraines? Significantly more vulnerable. But here's a number that really puts this in perspective. The range of vulnerability across the normal human population is about 10,000 to 1. 10,000 to 1. Some people simply cannot be made motion sick under any normal conditions. Others feel queasy just reading about it. And yeah, if that's you right now, I genuinely apologize. And then there's a whole spectrum in between. And interestingly, the one group with essentially zero susceptibility are people who have completely lost their vestibular function. No working inner ear, no motion sickness, ever, under any conditions, which is pretty solid evidence that the vestibular system is the core of the whole mechanism. The conflict needs two parties to argue, and if one party isn't showing up, there's no conflict to have. Now let's take a quick detour to outer space, because this is too good to skip. Roughly 60 to 80% of astronauts experience space motion sickness during their first 2 to 3 days in microgravity. Because in 0G, the otolith organs, those crystal and jelly accelerometers, are suddenly not being pulled downward by gravity anymore. They've been calibrated their entire lives to interpret a constant gravitational pull as "this is down." In space, that signal vanishes. The canals still work fine. Rotation still feels like rotation, but the otolith signals are completely alien, sending information the brain has no framework to interpret. The conflict is enormous, and the response is predictably unpleasant. Most astronauts adapt within a few days. Their brains essentially relearn what normal sensory input means in this new environment, which tells us something important. The brain can update its models. It just takes time and some deliberate exposure. This is actually why experienced sailors rarely get seasick anymore. even on rough water. Why fighter pilots can handle maneuvers that would incapacitate most people. The brain learned. It recalibrated. It updated its expectations of what normal movement feels like, and it stopped flagging the conflict as an emergency. So what does this mean if you're someone who struggles with car sickness or VR sickness? Yeah, we should talk about VR for a second. Virtual reality sickness is essentially the reverse problem. Your eyes are seeing fast, fluid movement through a virtual world, but your body is sitting completely still in a chair. The conflict is flipped. Vision says, moving fast. Inner ear says, absolutely stationary. Same argument, same poison detector alarm, same nausea. The practical advice, honestly, front seat over back seat, because you can see the road and your visual system gets better information about the actual movement happening. Eyes on the horizon, same principle. Fresh air helps, probably by calming down autonomic responses. Ginger has modest evidence behind it as a nausea remedy. Scopolamine patches work well for severe cases, blocking some of the signals that trigger the emetic response. And gradual exposure, short trips building to longer ones, genuinely helps your brain recalibrate over time. But look, the bigger thing here, the thing I find genuinely beautiful about all of this, is what it reveals about how your brain works. Your brain doesn't have direct access to reality. It never has. It only has data. Streams of signals from your eyes, your ears, your skin, your muscles, and it's constantly constructing the best model it can from that data. A simulation of the world, running in real time, updated every fraction of a second. And that simulation has assumptions built in, deep, ancient assumptions, shaped by millions of years of evolution for a very different world. And sometimes, the world moves faster than the assumptions. You're in a car. Your visual system is doing one thing, your vestibular system is doing another, and your brain, trying its absolute best with the tools it has, raises an alarm that made perfect sense 200,000 years ago. An alarm that says, something is wrong. Be cautious. Eject whatever might be causing this. It's not a malfunction. It's your brain caring about you ferociously, using the only playbook it knows. And it just didn't have cars in the playbook. That's what I love about biology. It's full of these moments where you realize that what looks like a glitch is actually ancient wisdom, slightly out of context. Your body is magnificent and a little bit confused, and it's doing its absolute best. If this kind of thing makes your brain light up, come hang out at Briefly Science. Subscribe, it's a 5-second click, and leave us a comment. Do you get motion sick? What's your worst story? Because honestly, misery loves company, and we're very curious.